Recording now.
Okay. Thank you, Raj, for a nice introduction and for giving me this opportunity. Title of talk is Recent Advances in Severe Plasticity, Strain-Induced Phase Transformations, and Microstructure Evolution at High Pressure with application to material synthesis, nanograined materials, and earthquakes. And I would like to acknowledge my collaborators, especially recent courses for this talk, and also funding agencies. And I will present today a first systematic in situ study of strain-induced phase transformations and microstructure evolution under high pressure and severe plastic deformations in three materials: silicon, zirconium, and olivine. And this will include funding first laws in this field and extraction of material properties, funding fields of stress and plastic strain tensor, and also mechanism, some theory, and with some applications. And at the end, I will show that even under hydrostatic loading, similar structural changes in plasticity are measurable in polycrystalline material as well. Well, processes involving severe plastic deformations. Processes involving severe plastic deformations and phase transformations at high pressure are widespread in science, engineering, and modern technologies in nature. It includes, for example, synthesis under static and dynamics high pressure, mechanochemical material synthesis, producing nanostructured materials by severe plastic deformation, processes in diamond anvil cell without pressure transmitting medium, and surface processing, friction, various military, geophysical, and other applications. And we're performing experiments in rotational diamond anvil cell. So two diamonds compress sample within or without gasket, like in traditional diamond anvil cell. And then we produce torsion of one of anvil with respect to another and superpose large plastic shear. This is very similar to high pressure torsion, which is routinely used to produce nanostructured materials, and there is very big community working on this topic. But here we have two advantages. First, we can study everything in situ under pressure and resolve everything along diameter. And also due to diamonds, we can reach much higher pressure. And we perform experiments at synchrotron radiation facilities at Ergon Laboratory at HPCAT. And we currently are using two static diamond anvil cell and two dynamic rotational diamond anvil cell. And just would like to mention that the first dynamic experiments here were performed by Arun Deverage. One of the main effects of plastic strain is that it drastically reduces phase transition pressure. And you see here some of our results in reduction of pressure by 1 and even 2 orders of magnitude. For example, graphite to cubic diamond transforms at 70 GPa under hydrostatic condition, and under shear it's 0.7 GPa. And if this process can be scaled up, this would be a new revolutionary technology of diamond synthesis. Then infinity means that these phase transformations were not obtained under hydrostatic pressure at any pressure, but we obtain them at quite low pressure with plastic straining. And key problem is that macroscopic thermodynamics fails to explain these results because yield strength and shear shear stress is limited by yield strength and shear, say 1 GPa. And if we include this in thermodynamic driving force for phase transformation, effect of shear stress is between 2 and 20%. So it does not produce such effect. And another problem was that before appearance of this paper, high pressure community did not realize difference between traditional pressure-induced phase transformation on the hydrostatic condition and phase transition which occurs during plastic flow. And pressure-induced phase transition start at pre-existing defects, which represent stress concentrator. And we introduced new concept of plastic strain-induced phase transformations under high pressure, which occur during plastic deformation and started new defects permanently generated during plastic flow. They represent defect-induced phase transformation and require completely different thermodynamic and kinetic description and experimental characterization. And the only defect which can produce such strong effects is dislocation pileup. And we first developed simple analytical model, but then much more advanced phase field model for interaction between phase transformation and plasticity. And let's consider material with properties close to silicon. On the hydrostatic condition, phase equilibrium pressure is 10 GPa. And if we introduce one dislocation, phase transition occurs at 16 GPa. Then we consider bicrystal under compression and shear, and dislocation nucleated grain boundary and pileup against grain boundary. And the tip of dislocation pileup, all stresses are proportional to number of dislocations, and it can be 10 and 100. So we have huge internal stresses here, which lead to lattice instability and barrierless nucleation of high pressure phase. And this happens at pressure average over the sample of 1.2 GPa. And this is conceptual proof that dislocation pileup indeed can reduce phase transition pressure by more than order of magnitude, and even almost order of magnitude below phase equilibrium pressure. And also important that phase transition is not localized at tip of dislocation pileup. With increasing shear, there is growth, coalescence, and quite large amount of high pressure phase. But plasticity plays dual role. It promotes phase transition by creating stress concentrator, but it also suppresses phase transition by relaxing these stresses. And in this paper, I made, based on simple analytical model, I made many predictions, and most of them were confirmed experimentally. But one of them was exactly opposite to what we observed in experiment. And problem is that based on SLB model for dislocation pileup, stress concentrator is proportional to shear stress and length of dislocation pileup. And length is usually fraction of grain size. So the larger grain size, the larger stress concentrator is, and the smaller phase transition pressure. And that is exactly opposite to what we observed in the experiment. Well, it's not shame to be full, but it's shame to remain full. So we need to fix this. And it took years to find out from much more advanced models, from phase field approach, molecular dynamics, and concurrent atomistic continuum approaches, the dislocation pileup at such large stresses are localized at grain boundaries. So length is much smaller than grain size. And that means it's not limited by grain size. And we have to consider model of super dislocation. In this case, number of dislocation is proportional to shear stress. Shear stress is determined by whole patch relationship. And when we put all pieces together, we obtain that the smaller grain size, the larger stress concentrator, and the smaller phase transition pressure. And this is exactly opposite to what we predicted here, but corresponds to experiment. However, with further reduction of grain size, we are in a region of inverse whole patch effect. That means yield strength reduces, and number of dislocation also reduces, because grain boundary sliding competes with dislocation activity. And that is why we predict that phase transition pressure will grow again. And this is exactly what we just obtained for phase transition from silicon 1 to silicon 2. You see in the region of whole patch effect for yield strength, for micrometer particles, phase transition pressure is 2.5 GPa, but for 100 nanometer particles, it's already down to 0.3 GPa. But if we further reduce particle size to 30 nanometers in region of inverse Hall patch effect, then phase transition pressure grows again to 5 GPa. So this is exactly what we presented, what we predicted, and this is first correspondence between grain size dependence of yield strength and strain-induced phase transformation. And this dependence is very unexpected because on the hydrostatic loading, phase transition pressure grows with reduction in grain size. And since we measure also evolution of crystallite size in each phase, I placed here also crystallite size at the beginning of phase transition, and the same rule can be formulated in terms of crystallite phase. Also, what is remarkable that for this phase transition, under hydrostatic conditions, phase transition pressure is 16 GPa, and with plastic straining is just 0.3 GPa. So it's 54 times reduction in transformation pressure, and it's the same under compression and compression and torsion, which is also remarkable. TM Fox says that there are no dislocation pileups for nanograin materials because they don't see them. And it's not surprising for us because in simulation, dislocation pileup is equilibrated by large shear stresses. And when we remove shear stresses, it disappears as well. So it should be detected in experiment, in situ experiment, but we don't know any method which will allow to do this. But we recently received very strong confirmation of stress concentrator, and as follows. So for pressure-induced phase transformation, pressure in high pressure silicon 2 phase is 2.5 GPa lower than in initial silicon 1 phase. And this is logical because of 22% of volume reduction. But what we found for plastic strain-induced phase transformation, pressure in silicon 2 is 5.7 GPa higher than in silicon 1. You see here 0.9 in silicon 1, 7.6 in silicon 2, 3.1, 8.5. And the same with further growth. And this is, this is direct proof that there is strong stress concentrator and it can be produced only by dislocation pileup. And this is consistent with result for 30 nanometer particles when dislocation activity is reduced. Here, a difference in pressure is just 1.4 GPa. And similar large pressure increase during phase transition, we observe also for phase transition from silicon 1 to silicon 3. You see here 4.6 and 11.6 by 7 GPa. So this is a very strong support to dislocation pileup based mechanism. And also what is important that, and we show it here with scale-free, with developed scale-free phase field model, that even in polycrystalline materials and quite small shear, we can reach quite large volume fraction of high pressure phase at low pressure. And some grains are completely are almost completely transformed, some just started, but with further plastic deformation, then will rotate, and further phase transition will occur. And even at 0.3, gamma of 0.3, volume fraction average of entire polycrystal is 0.6, which is very high. And this is summary of some other results for phase transition in silicon. For example, for 30 nanometer particles, silicon 2 does not appear at all on the hydrostatic condition, but we obtain it with plastic straining at 4.9 GPa. Also, nobody could retain silicon 2 because at unloading it transforms to completely different phases. But after plastic straining, we retain silicon 2, and in some region even poor silicon 2. Then also nobody could obtain reverse phase transition from silicon 2 to silicon 1, again, because other phases appear. And we obtain it because we obtain direct phase transition at a very low pressure, and other phases don't appear. Next, for on the hydrostatic compression for any particles, silicon 3 does not appear at all. And we obtained it with plastic shear at 0.6 GPa. And it's actually a very important problem now to quench and retain single-phase silicon 3, because usually it retains as mixture with silicon 12. And one of recent technology is quenching from 14 GPa and 900 Kelvin over 3 days, and some similar technology. And without any special efforts, we obtain pure silicon 3 by unloading from 11.6 GPa and in quite large region. And also after 4.4 GPa and small torsion, we retrieved a mixture of silicon 1 plus silicon 3. And because now it's clear that silicon 3 is also semiconductor, but with different properties, such nanocomposite may have useful properties. And yes, we measure evolution of distribution or volume fraction of each phase for each particles. And it's, I will not analyze this, but it's now, these results are now used for development of kinetics for this phase transition. And I will mention two other potential practical applications. First, very low phase transition pressure warns that some phase transformation may occur in NEMS, MEMS during contact interaction, friction, and they should be avoided. And also, usually silicon 1 is very brittle, and nanocracks appear during polishing. And they should be removed by chemical methods. That is why researchers develop so-called ductile regime of machining, when they utilize phase transition as mechanism of plastic deformation. But the problem is that in all simulations from atomistic to continuum, phase transition pressure is 10 GPa, but we obtain several phase transition at sub-gigapascal. So there is significant room here for improvement. Next topic is strain-induced alpha to omega phase transformation. And main basic problem in general in studying plasticity, microstructure evolution, and phase transformation is that they depend on all 5 components of plastic strain tensor, entire path, and pressure, which leaves little hope to find some general laws. Dependence on path means that if we compress and shear, or first shear and compress, or any intermediate combination, result will be different. And what I will show that we develop new in situ experimental and theoretical approaches, which should allow us to find first laws for each of these fields and for each of this process and for their interaction. And this is important. We start with strongly predeformed zirconium. So we produce multiple rolling until hardness, dislocation density, and crystallite size reaches steady state. And in such way, we exclude the effect on strain-induced phase transformation. And this allowed us to find something important, because otherwise it's complete mess. So this is kinetic equation for strain-induced phase transition. We derived it using micromechanics and all what included conceptual all what we learned at nanoscale. Time is not parameter here, and derivative is of volume fraction of high pressure phase with respect to plastic strain. And this equation is shown here as a line. And this is pressure plastic strain loading path. And here are 3 experimental loading passes. And all experimental results for this process are very close to our theoretical prediction. That means we conceptually proved validity of this equation and found all material parameters. Here is evolution of pressure distribution and volume fraction of high pressure phase for different loadings. And these squares are minimum pressure for initiation of phase transition at different loadings. And you see that minimum pressure is independent of radius. But plastic strain and plastic strain path differ significantly with radius. So at the symmetry axis, it's just uniaxial compression, and the magnitude of shear strain increases with increasing radius. And this independence means that minimum pressure for strain-induced phase transition is independent of plastic strain tensor and its entire path. And this is first rule in this field. And it has immediate application that strain-induced phase transformations under compression in traditional diamond anvil cell and shear in rotational diamond anvil cell don't fundamentally differ. And that means that we can study strain-induced phase transition in traditional diamond anvil cell as well. And that is what we used during COVID time. Of course, rotational diamond anvil cell are much more convenient for these purposes, because first we can independently vary pressure and plastic strain, and also we can not only initiate but also complete phase transition at low pressure. And shear stress or friction between diamond and sample plays crucial role in all these processes. And usual assumption was that friction stress reaches yield strength and shear, and this was used to determine pressure dependence of yield strength and shear. What we found that friction stress with traditional anvils hardly reaches half of yield strength and shear, and this shows error in previous work which determines yield strength and shear. And that is why we increase using several methods height of asperities for diamond anvils from 10, what was used before, to 300 nanometers. And with these rough diamonds, indeed, shear stress reach maximum possible value equal to yield strength and shear. And we slightly advanced non-equilibrium equation, which connects measured pressure gradient and pressure dependence of yield strength in shear. And here are several pressure distributions. And at each point, we have a completely different plastic strain tensor and entire path, and also different texture. So material is anisotropic, but still all this data can be described by such simple pressure dependence of yield strength, which is independent of plastic strain path, and does not show any signature of anisotropy. And that means that after severe plastic deformation and in given case phase transition, material behaves like perfectly plastic, isotropic, and strain path independent. And the problem is that everyone knows that after severe plastic deformation, there is texture. So how to connect this with isotropic behavior? And that is how we can do this. So here are usual yield surfaces which evolve. That means it depends on plastic strain path, and you see it shows anisotropy. But we introduce additional fixed surface, which is independent of plastic strain and plastic strain path. So it's by definition describes perfectly plastic behavior, and also it's isotropic for initial isotropic polycrystal. And what happens that during plastic deformation, after reaching some limit, actual yield surface reaches this external yield surface and then moves along it. And that is why material behaves like perfectly plastic, isotropic, and independent of plastic strain tensor and plastic strain path. And this drastically simplifies, this is also first rule for plastic flow on the severe plastic deformation, and it drastically simplifies experimental methods, theory, and simulation. And this perfectly plastic behavior is connected to microstructural evolution. For our purposes, we measured radial distribution of microstructural parameter. In given case, it's crystallite size. And you see here that it's independent after severe plastic deformation and phase transition. It's independent of radius. And that means that it's independent of plastic strain tensor, its path and pressure, and also we obtain that it's the same for smooth and rough diamond. This is first rule for crystallite size evolution measured directly in situ under pressure. And during phase transition, all these points collapse into one curve, which is a function of volume fraction of high pressure phase only. And it's also independent of plastic strain tensors, the strain path, pressure, and the same for rough and smooth angles. And this is first rule for evolution of microstructure during phase transformation. And this curve has important practical implication. You see, with quite high pressure for 14 GPa and severe plastic deformations, we cannot reduce crystallite size below 40 nanometers. And here, with very modest plastic strain and pressure range from 1 to 3 GPa, you see the crystallite size is 5, 10, 20s. So phase transition is much more effective and economic way to produce nanostructured materials, and also in given case to produce nanostructural composite because with optimal properties, because omega zirconium is strong but brittle and alpha zirconium is weaker but more ductile, and one can find compromise. And again, this economic way is possible only because we initially reach steady state by maximum by multiple rolling, and this reduces significantly phase transformation pressure so that we can run phase transition and low pressure. And the same we obtain for dislocation density. You see a steady state for after phase transition in omega phase, and unique curve during phase transition, curve as function of volume fraction, and both of them are independent of plastic strain plus strain path and pressure. And this plethora of results was obtained in a single experiment, thus transforming main challenge, strongly heterogeneous fields, into great opportunity to generate big data. But as usual, new results produce new problems. And problem is that we have now 3 steady states. First, after rolling with such dislocation density and crystallite size, and with rough diamonds, we obtain much larger dislocation density and smaller crystallite size than with smooth diamonds, which led to reduction in phase transition pressure by factor of 2, further reduction. And so this shows that rough angles produce different type of plastic flow, microstructure evolution, and phase transition. But problem is that is where we were till now. We had a single surface of perfect plasticity, but now we have 3 steady states with 3 different yield surfaces, yield strengths. So we have 3 surfaces. And each of them is claimed to be independent of plastic strain and strain path, which is contradictory. So key problem now for which classes of plastic strain path and pressure material behave along each surface and for which jumps from one into another. And this is unsolved problem. And only after it will be solved, we can claim that there is a consistent theory of plasticity for severe plastic deformation, because right now nobody knows which yield strengths for steady state should be used. And also, if we will solve this, we will be able to explain why different technologies like high pressure torsions, equal channel angular pressing, and their combination produce different steady grain size, and how actually to choose the deformation process to obtain optimal grain size. To develop science, we need to know all fields in a sample, including tensorial fields for stress and plastic strain components, and they are not measurable. So that is why we develop combined experimental, analytical, computational approaches to determine all fields and to extract all material properties. And even with experimental input, there is a problem. So traditionally, everyone measures radial pressure distribution in sample using distribution of volume of crystal cell measured with X-ray diffraction and equation of state determined under hydrostatic conditions. But it's well known that equation of state under hydrostatic and non-hydrostatic loading are quite different. And second, because we use axial diffraction and only crystallographic planes that are almost parallel to beam contribute to X-ray patterns, and axial strain and stresses don't contribute. And this causes significant error. That is why we don't use equation of state, and we measure an experiment distribution of radial and hoop elastic strain and use this as input. And well, we need to solve inverse problem, and to make solution more robust, we solve it in several steps. So first, we don't solve problem for phase transition. We take volume fraction of phases as input data from experiment. And we also develop analytical solution for stress field. And with this analytical solution and fitting to experiments, we determine friction condition, distribution of friction force, which we use in our finite element model as input data. And then with finite element, we determine all material properties and plastic strain and stress tensor fields. And we start with a very simple analytical solution, well known, it's Prandtl solution. And this is for plane strain and for infinite sample. And we accept a number of almost illegal assumptions to utilize the solution for our problem. So we introduce hoop stress in such way and transform problem to axisymmetric. We introduce pressure dependence of yield strength and heterogeneous distribution of friction forces here, which violate solution. And to make it even worse, we assume that this solution is valid not only for mixture, but also for each phase. And the only excuse is that at the end, we will show that analytical solution has good correspondence to finite element solution. To use this solution, we need to find distribution of shear stresses at the contact surface from experiment. And we use our measured distribution of elastic hoop and radial strains, and we decompose total strain or deformation gradient into deformation gradient under hydrostatic loading, and we know this from hydrostatic experiment, and then from deviatoric stresses, And for this step, we can justify general modified Hooke's law, which determines stresses based on measured elastic strains. And now we have a complete system of equations, and we determine stresses in each phase and at each point, and we determine friction distribution of friction stresses, and that is why we were able to find friction rules for alpha zirconium, omega zirconium, and mixture. And you see indeed that friction stress is smaller than half of yield strength in shear. And these friction rules we pass to our finite element model. And here is just quickly, it's nonlinear kinematics, Murnaghan elastic rule, yield condition, which depends on pressure and volume fraction of phases, flow rule, equilibrium equation. So we solve this problem with determined friction rule, and then determines the field of all components of stress tensor. And now first result is that if we don't do any simulation and use traditional approach, which we used before based on equation of state, then the minimum pressure for strain-induced phase transition is 1.36. But if we apply our method and satisfy all equation, it's 2.7. So correction is quite significant and important. And as I promised, you see here for shear stress and for two normal stresses, good correspondence between finite element solution and analytical solution for alpha zirconium, for mixture, and almost identical at much higher pressure. And it's always good to have analytical solution, especially that with analytical solution, we also determine stresses in each phase, but we cannot do this with finite element solution. So next step, we want to determine kinetics of strain-induced phase transformation. And in this case, we don't use experimental data as input data, but model kinetic of phase transition coupled to plastic flow. And this is our modified kinetic equation. So previously, what I showed, we determined kinetics based on data just at the center of sample, which means on the uniaxial compression. Because without simulations, we can determine plastic strain average over the sample thickness at the center only. Now we want to use data from entire sample on the complex compression and shear loading passes. And this term does not change. Here we had one, which means that deformation rate is 0 at completion of phase transition, but this is not the case. And we introduce here parameter and linear dependence of this coefficient on plastic strain and pressure. And then we find this coefficient by minimizing error. And if you see here numbers, we determine these parameters, and symbols are experimental data, lines are simulations, and you see very good correspondence between experiment and simulation, and differences within error of experiment. So we have now strain-induced kinetic equation. And since we choose that it's independent of plastic strain tensor mode and path, and we describe experimental data, that means that our kinetic is indeed independent of plastic strain mode and path. And we have also additional validation. This is for correspondence between finite element simulation and experiment for thickness profile, for distribution of elastic strains. And with such well-verified model, we can calculate all fields, in particular plastic strain tensor field for different loading stage, all stress components, distribution of volume fraction of phases, and accumulated plastic strain. So now we have complete information. And next topic is mechanism of deep focus earthquake. Deep focus earthquake occurs at such depths where pressure is 12 to 23 GPa and temperature is between 9 and 20 hundreds Kelvin. And usually it's assumed to be caused by instability caused by due to phase transformation from subducted metastable olivine to spinel. But there is no quantitative theory, and also there are various puzzles which were not explained. and some of them are here. So what are the mechanism or jump from geological to seismic strain rates, which is by 18 orders of magnitude? And how does olivine, which does not transform to spinel for over a million years, suddenly transforms within seconds? And how to explain shear-dominated seismic signal with volume change-dominated transformation strain during phase transformation? And in this paper, we develop a theory, and I will describe it shortly now, but the two main points. First, we treat phase transition in olivine like plastic strain induced instead of pressure induced. And this was not done for any geological material. And second, we found analytical 3D solution for couplet deformation, transformation, heating process in shear band. And this solution predicts first singular, that means infinite, transformation-induced plasticity shear, and also self-blown up deformation and transformation heating process. And both these processes allowed us to explain, to resolve these puzzles quantitatively, I mean to within order of magnitude, and explain the mechanism of deep focus earthquake. So this is a typical shear transformation band observed in a lab. It's 70 nanometers thick, and evaluated shear strain is 43. The transformation time is 3 seconds, and this is corresponding strain rate. In nature, thickness is much larger for transformation deformation band, and shear strain is huge, 10 to 6. And first here shortly, we check whether such jump in strain rate is possible without phase transition. And I will not go in detail. We use a generic equation which is used in this field for strain rate. And there are two mechanisms which allows strain localization and increase in strain rate. But altogether, it gives just 4 orders of magnitude increase in strain rate. And we found to obtain remaining 14 orders of jumping strain rate, temperature should be increased from 900 to 1800. And that is what we need to show. And this is thermal evolution, temperature evolution equation. This term is plastic dissipation, which is here. And this is heat flux from shear band, which is here. And intersections give two stationary solution. One of them, which is steady, which is stable, because heat flux from band is much larger than plastic deviation. Practically does not change, corresponds to practically initial temperature, no heating. And that means that without phase transformation or any other sources, heating is impossible because of very thin band. But if with help of phase transformation, an additional heat source, we reach second steady temperature, it is unstable because plastic dissipation is much larger than heat flux. And then further increase in temperature and strain rate will be possible without phase transformation. That is what we need to get. Increase in temperature due to phase transition to 1800 degrees. So as I mentioned, the first point is that this phase transition occurs during plastic flow. So it's plastic strain-induced phase transition. And we have to use our theory and our kinetic equation, which is independent of time, but depend on plastic strain. And this is equivalent form. dt can be eliminated. And it says that rate of transformation is proportional to rate of deformation. And if we put observable strain rate 10 over second here, we obtain here observable transformation time on the order of seconds. So this equation is consistent. This kinetics is consistent. And transformation-induced plasticity, or TRIP, is well known in geophysics. but it was neglected because it's really small. And this is true unless we consider shear bands. And here is shear band, and you see a portion of olivine isotropically transforms to spinel. And to restore continuity of displacement, this portion of material transforms to plastically deforms to such shape. And we found analytical 3D solution for these processes, and trip shear depends in such way on ratio of shear stress over yield strength and shear. And this is a red line. And in shear band, shear stress is equal to yield strength and shear, denominator is equal to 0, and plastic trip shear tends to infinity. And this explains everything. So it explains huge shear strain observed in nature and in lab, and also it explains shear-dominated seismic signal caused by isotropic transformation strain. But even more, so phase transition causes trip, but trip is plasticity. It causes again phase transition, again trip. So we have such self-blown up deformation transformation process. So these two equations should be solved simultaneously, and this is solution, and it's green line. And important point is that it also gives infinite plastic shear in a shear band. And then we need to evaluate the temperature increase due to trip shear. And we found that to get desirable 1800 Kelvin temperature due to trip shear, for phase transition, if phase transition occurs in less than 10 seconds, plastic required shear is very modest. It's less than 40, which is observed even in a lab. So this is consistent, and it's not a problem to get such temperature. And after this, plastic straining can occur with increasing temperature and strain rate without phase transition. This is summary of all processes. I will do this very quickly. So 2 key points. First, we consider phase transition as plastic strain-induced phase transition and use new theory. And also we found solution for trip in shear band, and it produces infinite shear. And their interaction produces self-blown up deformation transformation heating process. And in lab, there is no heating because shear band is very thin. And that is why measured shear strain is 40. But in nature, during this process, there is significant heating for temperature which exceeds 1800 Kelvin. And after this, further unstable plastic flow and increase in strain rate may occur without phase transition. And that is why shear strain is 10 to 6. And so we explain all puzzles, and it's quantitatively non-contradictory, and we just got first conceptual experimental confirmation. So under hydrostatic condition and room temperature, olivine does not transform to spinel at any pressure. And we obtain in rotational diamond cell with rough diamonds in dynamic cell, we obtain plastic strain-induced phase transition within 10 seconds, and at pressure as low as 15 GPa. So it's proper range. And we found first rules for this phase transition, that phase transformation pressure reduces linearly with increasing plastic strain and corresponding increase in dislocation density and reduction in crystallite size. Phase transition occurs directly to beta spinel, to gamma spinel without beta spinel. And we also found first rule for microstructures, that crystallite size in both olivine and spinel at severe plastic straining is getting steady and independent of plastic strain tensor and strain path. And spinel is significantly weaker than initial olivine. That is why we expect formation of shear transformation band, and indeed our finite element simulation for such case produce transformation shear bands and irregular distribution of average over the sample volume fraction, which mimics what we observe in experiments. So this is consistent with suggested mechanism, I mean our experimental results. And last point, very shortly, many high pressure researchers believe that if they use pressure transmitting medium, gas or liquid, this is clean experiment and everything is in under hydrostatic conditions. And only liquid and gas are under hydrostatic conditions. Sample is under non-hydrostatic condition because if it's polycrystal, and you see this is for zirconium again, initiation of phase transition pressure and entire kinetic depends on preliminary plastic strain significantly, and also during hydrostatic loading, before, after, and during phase transition, domain size changes significantly, microstrain changes, and dislocation density reach 10 to 15. So there are huge changes in microstructure and dislocation structure, and by definition, this is plastic deformation. So we have similar processes like under non-hydrostatic loading. Yes, they are less pronounced, but you see huge change in microstructure, in dislocation density, which means significant plasticity. And we found first rules which are similar to what we found on the plastic strain, that actually average domain size, microstrain, and dislocation density during phase transition are a function of volume fraction of omega zirconium only, which is independent of plastic strain tensor prior to phase transformation and independent of pressure. And well, in remaining -2 minutes, I will place conclusion. And main message is that I believe this is a new field of multidisciplinary research in situ study of plastic strain-induced phase transformation and microstructure evolution. And now we have first laws in this field, some hypothetical but supported mechanisms, some theory. And it has various applications in many fields, and various communities may be interested in this field. And I hope that it will be further developed. Thank you for your attention.
Thank you very much, Valery, for an indeed wide-ranging talk. The talk is now open for comments and questions. Just speak up, unmute yourself, put the question or comment in the chat, or raise your hand.
I'll ask a quick question. So you showed some like contour plots of the analytical solution versus the finite element for the different stresses.
Right.
I can't remember. It was back a while. I just had a.
Yes, for example.
Yeah, maybe even one before this.
One before. Okay.
Before this.
Yeah.
Yeah. So it was just looking like I was just curious, like if you look at sigma ZZ, for example, is it larger stress, I guess, it looks like it fits less well, but at the lower stresses, it seems to be even better. The same actually with the sigma RR as well. It seems like at the lower stresses, it does a better job. Do you have a sense of why the analytical solution seems to do a little bit better at the towards the right side of those than towards the left?
No, this is let's put in such a way. This is shear stresses. This is sigma RR. This is sigma ZZ. And this is for the same condition. This is when maximum pressure is 3 GPa. This is for small pressure at within alpha phase. Okay.
Right. So my question was like the green and the blue seem to be better reproduced than the reds do. on these two,
Uh,
on the sigma RR and sigma ZZ plot? Is there a reason why the analytical solution is closer to the finite element there?
Okay, let's put in a such way. Analytical solution predicts solution for infinite sample with large aspect ratio. So processes near center are not described by this analytical solution at
Okay.
all. And still we
Okay.
have something not very bad. But
Yeah,
at the
yep.
periphery also should not work well, but it works. But mostly this is, I would expect good correspondence somewhere here and for large aspect ratio. But it looks like that it works reasonably well for all cases, especially taking into account how many completely unjustifiable assumptions I made.
I like I like these analytical solutions a lot. So
Yeah,
thank you.
me too. I did not expect this.
Okay, thanks, Lowell. Wang, would you like to ask a question?
Oh, sure. It's Wu Yuan from GIA. At the very beginning, you mentioned that graphite could transfer to a cubic diamond, basically a diamond structure, under pressure like a 0.7 GPa within the sharing force environment. But at the hydrostatic is 70 GPa. Do you mean this is at the room temperature phase transformation?
Yes, this is at room temperature.
Okay. Yeah, very interesting.
Room temperature, no catalyst. And yes, and I can add that 0.7 GPa for cubic diamond, this is, it's retrievable. So also after pressure release, it was confirmed with TEM. Graphite to hexagonal diamond starts at even lower pressure at 0.4 GPa, but then it's much probably transforms to hexagonal and it's, sorry, to cubic, and after pressure release, it's not here.
At the bottom of this slide, is that the reference of this research?
Yes.
It seems you didn't. It didn't list the volume or title of this paper.
You know, this, okay,
But I will find it out since you listed the authors
okay.
and the
I
year.
did
I'll
not
find
discuss this today because I discussed this 3 years ago. Yeah, it's here. And because it's recorded, you can then check this with recording or make snapshot now.
Okay, thank you.
While you have this up, you made the statement early on that you need in general to go beyond macroscopic thermodynamics. There's a failure of macroscopic thermodynamics, and I'm trying to understand how general that is. Now, to what extent can you explain some of these just in terms of the change in enthalpy of the plastically deformed or badly deformed, destabilized lower pressure phase, which will obviously bring the phase transition boundary lower on hydrostatic compression?
Okay. Two points. First, if we are talking about nucleation, no chances. No chances, because here key point is what produces phenomena is that we apply relatively low pressure and yield strength, which is equal to yield strength and shear, macroscopic yield strength and shear, let's say 1 GPa, 2 GPa, right? But stress localization here could be huge if it's proportional to number of dislocations. So for example, you see here that average pressure, what we apply is just 1.6 GPa, but it's already phase transition, which requires 16 GPa.
Yeah, that's fine.
And this is because of local stress concentrator. So it's, and here also, we have concentration not only of pressure, but shear stresses. And shear stresses are not limited in this nanoscale region by macroscopic yield strength. they are limited by theoretical strength, which is 1 to 2 order of magnitude higher. So we can get this lattice instability and cause initiation of phase transformation due to this highly concentrated tensorial stresses. This is nucleation. Is it agreeable?
Well, no, that's fine. I'm asking a simpler question. Before there's any appearance of the high pressure phase and you have a destabilized sample, just from enthalpy measurements.
No.
Do you
Because-
see? Can you explain that? Because if you measure the free energy or the enthalpy of the two phases, the microscopic picture you're developing is fine. I'm just asking about treating this in terms of macroscopic thermodynamics. How far can you push that just from measurements, not from any kind of modeling?
Well, I don't. You know what? If you would measure this exactly at this point where there are huge stresses and would calculate this enthalpy here, that is what model does actually, then it's okay.
Okay.
But what you usually measure is average over the entire sample, right? Macroscopic sample.
Right.
And then change in enthalpy due to plastic strain is not significant.
Okay, well, we
It's
can.
not significant. So
we
this
can take
is
this
the
up
point.
offline, but that's very interesting. Okay, Magali, would you like to give a comment or
Yes.
question?
Hello, Valerie. It's
Hi,
nice to see
Magali.
you again. So I wanted to ask a question about the deep earthquake application. And in particular, I'm trying to understand how we deal with the much slower strain rates that are occurring. So I understand that this mechanism is basically dependent on strain and the strain accumulation. But because the strain rates are so much slower in the real in the Earth, how are there not other relaxation mechanisms that then become important on the much longer timescales? Because we're relying on these dislocation pileups, right? But now you have to build up these dislocation pileups at a much lower strain rate, and to build up enough shear to initiate the instability. And so are there just not other mechanisms available at these temperatures to relax these dislocation pileups or do some sort of healing process?
Yes, it may be, but I consider multi-stage process. So first, it's that is what I actually omitted. But first, there is a slip system which has 3 times lower yield strength. So first, I expect some strain localization, potential strain localization, if we will, if this slip system will be aligned.
Okay.
Right, in several grains. Then it will be just simple shear. It cannot provide all 5 components of plastic strain, but it can provide plastic shear. Then another step is that olivine is mixed with other minerals like diopside, which is much stronger. So then localization may occur, further localization may occur in the region with low content. Local regions with low content of diopside. And this already increases strain rate by 10 to 4.
Okay.
Then, this mechanism may be violated, but at least if you have aligned weak slip system, then it's reasonable to expect that plastic straining will occur along the slip system. Okay.
Right.
And it's slow,
Okay.
and then it can slow start phase transition, and then during phase transition will be this cell blown up process, which will increase temperature. But by the way, this temperature, let's say in our initial temperature, what we take 900 Kelvin, and melting temperature is 27. This is low temperature regime. It's less than recrystallization temperature. And then when we get to this temperature, I expect after this temperature, we don't need phase transition at all. But here, traditional mechanism may already play a role, because at this temperature, kinetics may be fast enough to produce phase transition in second. But we don't need this. It's already
No.
end of story.
Okay. There's another question in the chat that's related to this about like, how do you scale up in terms of size? That I wonder if you could answer that as well. Thank you.
What exactly?
It
What
says,
is-
you have a very, your experiments are done, I think, on very small,
Right.
shear, right? But you expect your faults to be thicker. All right, the shear zones in nature will be much thicker. And so how
Yeah.
do you deal with that part?
Okay, that is what I told that in a lab, because it's very thin. We don't expect heating. Even with this process, with phase transition, with strip, we still are at low temperature. But phase transition and trip occurs. And that is why plastic strain is estimated is 40. And that is what is observed in previous experiments. Just 40. It's not much. It's not temperature promoted. But in nature, and the simulation shows this. I'm scale up with simulation. So when I do simulation for sizes in nature, and this is several millimeter, then we obtain temperature growth. It's easy to get this 18 from this equation, right? When we substitute parameters for shear band thickness in nature, then it's easier to obtain, to get this 1800 Kelvin, even by plastic strain smaller than 40, which is observed even in lab. So then in nature, it's not a problem to get this, but after this, we don't need phase transition. And then it's just unstable thermoplastic flow. And that is why shear strain is much, much higher, which is for what I mentioned, 10 to 6. So scaling here is with this simple simulation, with this simple analytical solutions.
Thank you.
Okay, thanks very much. There's another question in the chat from Patrick Cordier. Do you ever find evidence of amorphization during severe plastic deformation?
Yes, we found amorphization in silicon carbide. It was a while ago. Let me see. For silicon, there was amorphization for 30 nanometer particles. For 30 nanometer particles, even under hydrostatic, even under hydrostatic loading and unloading. And this is slow unloading. And I believe that, well, I know a lot of data that, for example, nickel titanium under severe plastic deformation, nanocrystalline nickel titanium undergoes amorphization. We did not observe plastic strain-induced amorphization in silicon. But honestly, we don't produce very large plastic shear for these experiments because we obtain all effects, all what we needed at moderate plastic shear. And because, if we do measurements for each condition, we do measurements along diameter. This is like 60 points. So if you would go to very large shear, then we need to increase step between shears. But we wanted to study this in more details. And what I expect that when we will increase further strain rate, we will get amorphization more easily for more cases, in particular for silicon.
Okay,
Thank you.
There's another question from Wayne Chin. For the earthquake study, would phase transformations induce electric charge release? Also, you covered the large strain rate gap. What do you plan to cover in terms of the size gap? And that was something you addressed earlier from your lab.
Yeah, I address this. This can be done only through simulations, I believe, because, maybe in large press, sample size can be increased and maybe heating will be absorbed also. Yeah, maybe.
And as for the first part, the electric charge release, I mean, you in principle could study the dielectric properties across the phase transition if you had a sensor present.
Yes, we did not do this. I believe we have enough for what to measure at given point.
Okay.
Yeah, but I agree that this may be important. I agree.
Okay. I particularly like your last point regarding the non-hydrostatic effects that appear in quote unquote hydrostatic experiments, because people often assume that because you have a hydrostatic medium, you will have a hydrostatically compressed sample. But you made the point that it's not the case when you have a phase transition or a microstructure developing across a phase transition.
Yeah, this is very important, and I would like to stress even before phase transition. So this is, for example,
Right.
Increase in dislocation density under what we call hydrostatic loading to 5 GPa before phase transition started. And this is for plastically predeformed material, and it grows from 6 to 1.1, 10 to 14. And this is 1 over meter square. And such dislocation density is goal of community which produce nanograin materials and with severe plastic deformation. So even just under hydrostatic condition, it grows significantly.
Right.
And here it grows more than, I don't have numbers, I believe, or it's difficult to remove all this stuff. But here is even larger for annealed material, and this is clear that change in dislocation structure is larger because yield strength is lower. So there is more significant plastic strain, and this comes from grain boundaries, from triple junctions. So there are a lot of from heterogeneous orientation of grains, and then it develops internal dislocational structure, and all this change in dislocation structure is plasticity. Yeah, I agree.
Another
This
question.
is
There's one from Ben Hur.
Yes. Hey, Prof. Thank you so much for your great presentation. I have a question regarding probably your future work. So do you want to, for example, do some other experiment or simulations for considering high strain rate loading? And in that case, is the sequence of, for example, the phase transformation or deformation mechanism would be important? For example, maybe in some cases we have amorphization, for example, before virtual melting or other kind of phase transformation. In that case, so how would you try to resolve the sequence of the phase transformation in the materials that you're gonna do?
Yes, actually, this is what is planned to do in our current project from Metal program. And we already have tool, dynamic rotational diamond anvil cell, which allows rotation up to 4,000 rotation per minute. So then question will be how fast measurements in situ measurements can be produced. And I am absolutely sure that strain rate will affect sequence of phase transition, and of course it may affect mechanism of plastic deformation, and amorphization will be observed more often, and time effect of different time scales, relative effect of time scales. So typical time scale for plasticity, for phase transition, and for various structural changes. This interplay will be important and will determine all phenomena. Yes, we plan to do this. This is, and we have current project, and we have several proposals for other material systems, for ceramics, and yeah, hopefully we will get something for geological materials. Till now we did not But yes, this is very important.
Thank you so much for explanation.
Okay, if there are no more questions or comments, thanks, Valery, for a very interesting talk. Great discussion afterwards. And we had up to 86 participants at one point. So it's a good sign for the webinars for this coming year. So thank you all for joining us.
Thank you very much to everyone, and thank you, Russ, for giving this opportunity again.
Yeah.
Bye.